Paper's made of cellulose, which is insoluble in water and most organic solvents. However, by chemically modifying it, it's possible to change its properties. A very common way of doing this is by acetylating the glucose subunits that make up cellulose. It's sometimes done completely to form cellulose triacetate, but it's more common to do it partially. The partially acetylated cellulose has on average 2 acetyl groups per glucose unit and is often just called cellulose acetate. In this video though, I'll refer to it as diacetate to make it more clear which one I'm talking about. Anyway, both these forms have slightly different properties which make them better for certain applications. In both cases though, the general result is a synthetic cellulose derivative that can be dissolved in organic solvents. Once dissolved, it's usually spun into fibers or made into plastic films. The diacetate has a much lower melting point, so it can also be liquefied and then injection molded. Over the years though, these cellulose acetates have been slowly replaced with newer and superior polymers. Its use now is quite limited, where the triacetate is mostly used for packaging, membrane filters, and some photographic film, and the diacetate is used to make things like toothbrushes, eyeglass frames, and cigarette filters. Still though, I thought it would be something interesting to explore, so for this video I'm going to be making both types and testing out some of their properties. In terms of supplies, I'll be needing acetic anhydride, acetic acid, sulfuric acid, and a source of cellulose. I'm just going to be using filter paper, but in theory it's also possible to use cotton balls or something else. To get things started, I cut up the filter papers, weigh out 10 grams, and add it all to a flask. I squish it all down with my glass rod, and I added a mixture of 50 ml of acetic acid and half a gram of sulfuric acid. I mix it around for a couple minutes just to make sure that I wet all of the paper. Then I let it sit for about an hour with occasional stirring. What I'm doing here is a pre-treatment, and it helps open up the normally tightly packed cellulose fibers. This allows the fibers to be acetylated more evenly, and it'll also speed up the reaction. So an hour later, the pre-treatment is done, and now it's time to acetylate it. To do this, I add a mixture of acetic acid and acetic anhydride, cover the top, and put it in a hot water bath. I also added a thermometer, but that wasn't really necessary. The water bath's held at a stable 50 C, and the flask is kept here for the next 30 minutes or so. What's happening here is a reaction between the acetic anhydride and the hydroxyl groups of cellulose. Each glucose subunit has 3 hydroxyl groups, and almost all of them will get acetylated. This type of reaction is known as an esterification, and it leads to the formation of cellulose triacetate, which is soluble in the acid mixture. So, as the reaction progresses, all of the paper should slowly disappear. If it doesn't, it's probably because the pre-treatment wasn't done properly. I did a couple runs before this one, and I found that if I didn't coat the paper really well, there was a lot left over. After 30 minutes, I take it out of the hot water bath, and I separate it evenly into 2 round-bottom flasks. The solution at this point is still quite cloudy, but I tried vacuum filtering it, and it didn't really work. It was taking forever to pass through the filter, and the stuff that came through was almost just as cloudy as the stuff I started with. Unfortunately, this will almost definitely affect both the quality and the purity of the plastic that I make. So if you guys have any ideas on how I could clear this up besides using vacuum filtration, I'd love to hear it in the comments. Anyway, what I'm going to do now is process what I have here into the 2 forms of cellulose acetate. I'm going to make the triacetate first from the one on the left, so for the time being, I just cover the one on the right with some plastic. Making the triacetate is easier, and the first thing I do is put it back in the hot water bath and add a stir bar. This time though, the water bath is slightly hotter and it's held around 60 C. Then to this, I pour in 25 ml of 80% acetic acid. The other 20% of this is just water, and up until this point, everything was completely water-free. The purpose of adding it now is to destroy any excess acetic anhydride that remains after the reaction. I can't just add pure water here because it could cause the cellulose triacetate to fall out of solution. If enough falls out, the whole solution could freeze, and this step could get messed up. The extra acetic acid just helps to keep everything dissolved. After the addition, I keep it here for about 15 minutes, and then I pour it all into a beaker. I slowly mix in about 25 ml of distilled water, and a whole bunch of triacetate starts to appear. Then on top of this, I pour in 200 ml more to completely knock out the rest. I mix it up really well, and I let it sit for a couple minutes. To separate out the triacetate, I just dump it into my vacuum filter and I turn on the pump. All of the water is quickly pulled out, but unfortunately, this is the beginning of the kind of annoying part. The reaction mixture that I'm filtering off is highly acidic, and well, this gets all absorbed into the cellulose. So just pulling away the water isn't good enough, and there's a whole bunch of acid that's still trapped inside. And unfortunately, it doesn't go away with just one washing, and it takes several. There's also no way to know exactly how many it'll take. I basically just need to keep doing them and testing the pH of the water that passes through. I know I'm done when the pH paper tells me it's neutral or only slightly acidic. When I get to this point, I stop doing the washes and I leave the pump on to dry it up as much as possible. I then transfer it to a watch glass, but at this point, it's still really wet. It did have an interesting texture though, and it was kind of a mixture between wet paper and dough. Anyway, for the time being, I put this to the side and I move on to making the other form of cellulose acetate. For this one, I need to add a lot more liquid to it, and I was afraid that it would overflow the small flask. So just to be safe, I transfer to a much larger one, and I also drop in a stir bar. I wait for it to warm up to about 60 C, and then I add a dilute mixture of acetic acid with a small amount of sulfuric acid. By adding water here as well as sulfuric acid, I'm going to be hydrolyzing some of the acetyl groups and converting them back to hydroxyls. I'm going to run it under these conditions for about 3 hours, which should on average remove one acetyl group for every glucose unit. So the major product I'll be making is cellulose diacetate, but I'm sure some triacetate will remain unaffected, and I might also form some monoacetate. When it's done, I transfer everything to a beaker, and from this point on, the workup is exactly the same as the last run. I slowly add 25 ml of distilled water, with stirring in between. In the previous run, it seemed like once the precipitate appeared, it was there to stay, but this time, it all redissolves back into solution. To really knock it out, I have to add a bunch more water, so I pour in 200 ml. I mix it thoroughly, let it sit for a couple minutes, and then transfer it to my vacuum filter. I pull away all of the liquid, and then just like last time, I wash it several times with a whole bunch of water. I leave the pump on to dry it up as much as possible, and then I dump it out onto another watch glass. To get rid of the water in this and in the triacetate, I put them both in my toaster at a low heat for a couple hours. When they're both dry, I'm left with some nice hard and crunchy powders. The stuff on the left is the triacetate, and for some reason, it's slightly yellow. I think that it might be like this because maybe I didn't fully wash out all the acid, but I'm not exactly sure. In any case, I'm going to move on and do a quick test on both of them to see if I did in fact make the two forms of cellulose acetate. The test is really easy, and I just need to see if they dissolve in acetone. So I add a small amount of each to 2 test tubes, followed by an equal amount of acetone. I ended up adding more acetone to speed things up, and all of the diacetate eventually dissolved. However, most of the triacetate still remained. This is exactly what's expected to happen, and it confirms that I did make 2 different products. Anyway, now it's time to make some plastic. I tried to find some info or detailed procedures on how to do this, but I wasn't able to find much. So most of what I'll be doing is just messing around and trying out things that I think might work. I wanted to start by making plastic films, and I first tried it out with the diacetate. I threw a random amount that I felt was enough into a beaker, and then I shot in some acetone. The quantities here aren't super important, and I'm just trying to make a really concentrated solution. It took quite a bit of stirring and something like 5 minutes, but eventually everything disappeared. I could probably dissolve more, especially if I warmed things up, but I figured this was good enough. To make the films, I just need to pour it out and let it evaporate on something, but I wasn't sure what it would work on. I just had to try it out for myself, so I poured some onto aluminum foil and the rest into a glass dish. Then I just waited for the acetone to evaporate, which took quite a long time. What's kind of interesting was that as it evaporated, the cellulose acetate slowly contracted in on itself. It's happening in both samples, but the aluminum foil one is much more evident. Eventually, the acetone was pretty much gone from both of them, so it's time to check them out. I first look at the one in the dish, which turned out way better than I expected. I honestly thought it would just stick to the sides and be a complete mess, but it was extremely easy to remove. It's definitely not the most beautiful piece of plastic, but I was still pretty impressed by it, considering it did come from filter paper. In terms of strength though, it's quite brittle and it breaks very easily. When I go to just bend it a little, it completely snaps in half. I tried bending and testing one of the halves, and at first it seemed to be a little bit more flexible, but then it quickly broke. Now over to the aluminum foil run, and it's a complete piece of garbage. Not only does it stick to the foil, but the film that it produces is uneven and pretty ugly. It might be able to fix this by first applying something like petroleum jelly, but I didn't try that out. I figured that even if it did work, it would be at best just as good as the glass dish, so it wasn't really worth it. Anyway, what I wanted to try next was to see if I could make the plastic less brittle by adding a plasticizer. The phthalate-based plasticizers are the most commonly used ones, but unfortunately I didn't have any. I was able to find a paper though that talked about replacing the phthalates with triacetate, which is something that I have. The triacetate is an acetylated version of glycerol, and it's a lot more environmentally friendly. The paper talked about a couple different plasticizer ratios that could be used, but I decided to go with 20%. I went with 20 because it seemed to offer a good combination of strength as well as flexibility. Anyway, just like before, it was all dissolved in a minimal amount of acetone and then poured into a glass dish. I wait for all the solvent to evaporate, and I remove it from the dish. Parts of it were still pretty brittle, but in general, it was a lot more flexible. The quality of my film is definitely still not very good, but you can see that the addition of the plasticizer did get it closer to being a usable product. I think the reason why it's still kind of brittle is because of the low quality cellulose acetate I'm using. Even after everything was dissolved in the acetone, it was still a cloudy mixture because of a bunch of impurities. As the film forms, the impurities get incorporated into it, and I'm sure they impact the structure and quality of it in some way. I didn't want to completely break it into pieces like the other one, but I did snap off a small portion of it. This small section was extremely flexible, but it was also pretty strong. I was able to completely bend it in half, and I didn't even feel like it was close to snapping. As a final test, I pulled it apart, and it wasn't very elastic. Anyway, I moved on to trying the same things with the triacetate, except this time I can't use acetone. The triacetate isn't soluble in it, so instead I use a mixture of 9:1 DCM to methanol. I started with a bit more solvent than I needed here, so I just kept adding the triacetate until I got to a saturated solution. I poured it all into a glass dish, and this time I decided to do a time lapse. I also wanted to see what would happen if I lightly blew on it with a fan, and the answer is that it's not good. The solvent evaporated off way too quickly, and the triacetate contracted in on itself. By the time all the solvent disappeared, what I was left with was really sad looking. I decided to take a closer look anyway, and as I expected, it was really brittle. There was little to no flexibility, and it snapped and shattered with only a bit of bending. What's kind of funny is the small remains that were left in the beaker actually gave better results. It was still brittle and useless, but clearly slow evaporation was important for getting a good film. I then did it again with a 20% mixture of triacetate, and I let it evaporate very slowly. The film it made was quite strong, and it seemed to be more flexible than the diacetate was. I think this film might have just been thinner though. Anyway, keep in mind that the stuff I'm using isn't super pure, and that the impurities might affect the final properties of the plastic. I did a bunch of other runs besides the ones that I showed, but they weren't too interesting. With the stuff that remained, I wanted to see if it were possible to dissolve everything and then mold it into something. So I added all of it to a beaker along with the triacetate. Then I added the solvent in small portions until pretty much everything dissolved. When I was done, I was left with a viscous solution that would quickly freeze when even a small amount of the solvent evaporated. In my older video where I made soap, I also made a mold of the caffeine molecule. I carefully poured in the cellulose acetate, and I tried to make sure that there were no air bubbles. I still had quite a bit left over, so the rest of it was poured into another mold. I waited a couple days and then I went to demold the caffeine molecule, but I could immediately see it was a failure. As the solvent evaporated, everything contracted like we saw before, and since it was held in a confined space, it ended up cracking itself. I thought it was done, but I could still smell some solvent coming off of it, so I let it sit out for another day. It ended up contracting even more, and in doing so, it curved inwards. It was extremely fragile, and with very little effort, it easily broke into pieces. When I came back to the other molds, they'd shrunk a whole bunch, but they actually kind of turned out. The butterfly one wasn't very strong, and with just a bit of force, I was able to crack it into several pieces. The ladybug was a lot tougher, and it took a lot more effort to break. When I finally got it open though, you can see that it's not solid inside, and there are many hollow spots. This clearly isn't the best way to mold cellulose acetate, and it's the reason why it's usually just melted instead. Then the liquefied form is either extruded or injected into a mold. I'm not really sure why, but when I first started this project, I didn't really have any plans to try melting it. At the last minute, I decided that I would, but I now have a problem. At this point, everything I have is a mixture of the dye and triacetate, but only the diacetate is really gonna melt properly. I figured I'd just try it out anyway though, and see what happens. I just threw all the small pieces of the butterfly into a test tube and blasted it with a heat gun. The major problem with this method is that good and constant temperature control is almost impossible. To get a good quality plastic, the temperature must be raised above the melting point, but it can't go over its decomposition point. Also, one other thing that I should mention is that cellulose acetate doesn't really melt on its own, and it needs to have a plasticizer. The stuff I have here is already 20% triacetate, and I just want to see how it would turn out. After a couple minutes, it was a gooey blob at the bottom, and I think it's a mixture of liquefied diacetate and semi-solid triacetate. I let it cool down, and then I smashed the tube with a hammer and recovered the small piece of plastic. Although it turned brown, probably because I heated things up a bit too much, I was still pretty impressed with it. I was curious to see how durable it was, so I got my hammer. Unfortunately, with just a couple small taps, it crumbled into pieces. Its lack of strength, I imagine, mostly comes from the terrible heating method and the presence of a lot of triacetate. As another test, I thought that maybe the brittleness could be helped by adding some more plasticizer. So I collected the broken pieces of my caffeine molecule and added a whole bunch of triacetate. Then, just like before, I melted it down into a gooey mess and let it cool to room temperature. This time though, when I smashed the test tube, I ran into a problem. With the added triacetate, the cellulose acetate became a lot stickier and softer, and the glass didn't really want to come off. I tried to remove some of the glass manually, but the thing kind of just started falling apart. I went to do another hammer test, but smashing it this time doesn't really make any sense, so I just squished it. These two runs didn't exactly give me the highest quality cellulose acetate, but they did highlight how important the plasticizer is. With not enough, we get a plastic that's too brittle, and with too much, we get one that's soft and not very durable. For one final run, I used the remains of the broken ladybug and just added a couple drops of triacetate. In my opinion, the final product was pretty cool, but just visually, you can see that it's not very strong. There's clearly a lot of cracking already going on, and I think if I just dropped it or something, it might break apart. Anyway, I think that's about it for now. In the future, I might try to make cellulose acetate again, and I'd love to hear what you guys have to say about how I could maybe do this better. Also, if you know a way that I could spin the cellulose acetate into fibers at home, I'd love to hear about that as well. As usual, a big thanks goes out to all my supporters on Patreon. Everyone who supports me can see my videos at least 24 hours before I post them to YouTube. Everyone can directly message me, and anyone who supports me with $5 or more will get their name at the end like you see here.